Hello and welcome to 14th lecture in 19th chapter of our comprehensive course on AI, ML and DS. Now here we want to talk about some more statistical distributions which are in this diagram. However, we will not talk all, but we will only take those which are useful from data science point of view. Okay, so some such data distributions are, I have given these two links. One of the link is that Statology that we already know. It is a good website, I told you. But the second link, this Buffalo University's probability playground. Now this is also a very nice uh, website. For example, just earlier we have done some distributions, so we can just use that website to verify or to view them and get some more information. For example, uniform exponential normal. Okay, so here I can select any distribution. You can see the long list of available distributions. So I take uniform AB distribution like that. Okay, uniform, and that is as I have shown here, uniform. So it is that kind of distribution, right? This kind of, and I can even vary these parameters like A and B bring closer, A and B bring away from each other, like that. I can write PDF, probability distribution and cumulative distribution function of that uniform distribution, CDF. I can visualize this way and simulate also that what is the way in which uniform distribution. So if X is chosen randomly from A and B, and they are allowed to fall just randomly those selected numbers between A and B, then they will automatically arrange themselves in this manner, right? Okay. Now I pause my video. Okay, this is the intermediate stage after several seconds, maybe I think 200 seconds I paused my video. Okay, so you can see that these are numbers which are between minus 2.636 and plus 2.636, and they are falling randomly, any one number between this number and this number through a sieve like thing maybe, and the sieve is having pores, so the number straightway goes down. Then this kind of distribution is created, and if I allow it sufficiently, then you will see that you can imagine that it will be a horizontal distribution like this kind of case, right? So a horizontal distribution will be seen, correct? So this is one. Then similarly exponential. So in this now choose that exponential beta distribution, right? And visualize maybe okay, simulate. So this is how the exponential distribution is created. That is distribution according to this mathematical function. This mathematical function 1 upon beta into e to the power minus x divided by beta. And again I can pause this for a long time and show you final, but now I am not waiting that much, but I just show you the final PDF. Okay, so it will be this kind of graph, that is clear, right? So okay, next there was this normal distribution, our famous and the most important and the popular. So normal distribution, and again I can, this kind of graph should be created. So simulate, that is that sieve or popcorn, that kind of example. So if you freely throw the numbers uniformly between this and this, minus 10.95 and 10.95, then they will arrange themselves in normal distribution like this. Okay, so that is also, I'm stopping at this point and just means I'm not pausing, I'm just stopping the simulation and show you this kind of graph is created. Similarly, there is discrete binomial distribution. So here I can find that binomial. In binomial, there are many beta binomial and all that. So I take this binomial NP distribution and simulate it. This is the original PMF, okay, probability mass function it is called. Okay, and this is the simulation. Bernoulli trials, that is the coin toss trials, are being run, and how many times head is obtained, that is what you are finding. Say 1 is equal to head on the right side and 0 is equal to tail. So initially it looks that tails are dominating, but as the number of trials become larger and larger, ultimately both these vertical bars will become equal. So the probability of getting tail and head both are equal. You can see that it has already started attaining this kind of shape, right? Okay, fine. Now then this is geometric distribution. So this geometric is here, because it is not important to remember the equations, rather it is more important to remember the feeling for that kind of distribution. Geometric distribution, that is how many trials would be required before getting the first successful event, right? For example, in A/B testing, before conversion, how many windows will the visitor move through? Or in marketing, how many prospective customers you would have to meet before getting your first successful paying customer, and so on, right? Fine. Now this is geometric distribution. Then there is another which is hypergeometric distribution, correct? So for hypergeometric distribution, this, okay, and here I am simulating. So this kind of graph would be created. Now you can see that graph has already started forming. Initially it looks uniform, but still the tail is created on this side first. Okay, and if I draw its probability mass function, then here it is uniform, but I can try changing this way, this kind of, okay, just to match with that. These are various parameters or constants. So now it is matching with this distribution, right? Geometric distribution. So geometric is this, okay. Then you can clearly see that it is that geometric distribution and hypergeometric distribution. So hypergeometric distribution, okay. And then what this was binomial that we have done, okay. So we have done all fine. Now similarly, now we want to talk about some extra new distributions, but these are also only those which are useful, okay. We will not discuss all of this, but you can find each of these in this website, and the link is given in the Jupyter notebook, so you can use that link, and it is a nice probability playground of Buffalo University, okay. So that is this I am closing, but this chi-square distribution. Now chi-square distribution is used to model the sum of squared deviation, and it is used in hypothesis testing and variance estimation. What is its real life example in data science? And this is important, that chi-square test is often used to evaluate the relation between categorical features and the target variable. For example, we were doing one particular project for property price prediction of India's six metro cities, that is Delhi, Mumbai, Kolkata, Hyderabad, Chennai, and Bangalore. And I had the data, real data of all these six cities, and I was asked to build a predictive model, deploy it on cloud, and including the user interface and everything. Right now, first I have to decide whether the property price depends on city. So at that time, each city name that will be six features. So city Chennai, city Bangalore, city Mumbai, city Kolkata, and so on. Six city names. They are six features. So I conducted the chi-square test so that I wanted to know that whether property price is significantly affected by changing the city. Now, our common sense is that it is affected. That means the property price in Bombay follows different logic than maybe property price in Kolkata. But that is common sense. Anything is not acceptable in data science. You have to actually work and show by some statistical or that kind of test, and that result should whatever that result tells, that is whatever your data tells, that is final. So my data told me that yes, if I take different categorical feature, that is city Mumbai and city Kolkata, then its relation with the target variable. Target variable was the price of the property which I was predicting was different. So that means that I got the idea. Not only that, inside each city there were observations for different localities. For example, in Mumbai there were observations for Bandra, then there was observation for Juhu, Borivali, Andheri, then maybe other parts of Bombay. Now I want to check again whether these locations matter or not. Again, it is a common sense that in property the location is the most important. For example, Bandra and Juhu, particularly Juhu is the abode of rich people, film stars and big industrialists and also so on. So obviously it should matter, property price should matter, right? But on location. But still I conducted the chi-square test and found that if I take location Bandra inside Mumbai and location Juhu inside Mumbai and location Andheri, then I found that the target variable varies significantly. So therefore I decided that I will have to make a user interface in which user will first select his city, then he will select his location, and then he will do this property price prediction. Okay, so that is a chi-square test, and here you can do the chi-square distribution somewhere here, right? So this kind of typical graph is seen. Now this is a chi-square graph, this is also a chi-square graph, this is also a chi-square graph. So you should not have wrong idea that only this is a chi-square graph, depending upon the value of these constants in the equation. Okay, so the chi-square graph keeps on changing, correct? So it may be this way, like that. But what is the use of this chi-square graph? That is important. Okay, and here also if I simulate it, then you will see that this kind of graph will be obtained, which is a typical chi-square graph. Okay, this kind of graph is obtained. Long tail, okay, on right side. But that is, as I said, just one of the case. You can have almost symmetric, looking like normal, but still there is a tail on right side. Okay, and you can have this kind of also almost looking like exponential curve, but this okay, but it is actually a chi-square curve. Fine. So that is one thing. Don't worry, you will not have to identify that whether this is this curve or this curve. So that mixing will not happen because that is also done by algorithms itself. That is Pareto distribution. Now this is also one very useful distribution from data point of view. Pareto distribution. What Pareto distribution says, or what Pareto principle says? Pareto principle says that 20% of the best independent variables are responsible for 80% of the outputs in many situations. What are examples? So it says that for any big firm, 20% of the large customers, they are responsible for 80% of the business. So normal customer service adage is that customer is king and all that. But sometimes you find that companies behave very rudely with you, and you think that what is this? They say that in market economy, customer is king, but this company seems to be completely uninterested in retaining me as a customer. Then you have to accept the harsh reality that you are not big enough customer for that company. Okay, so companies also know this, that their 80% of the business is coming from 20% of the important customers. So if you fall in that 20% of important customers, then they will treat you properly. But if you don't fall in that 80% of the important customers, then in that case, fine. Okay, you can expect an average customer service. That is all. Okay. Similarly, other example of that Pareto principle is that in software development, 20% of the excellent programmers are responsible for 80% of the quality improvement in the software. Similarly, when software crashes, 20% of the bugs are responsible for 80% of the crashes. Similarly, in the income, then income distribution in any country, particularly in capitalist country, always goes like this. So there are always 20% of the people that occupy 80% of the wealth. And as the income inequality goes on increasing, this graph may become even more sharper. Don't have the provision to make it further sharp, but as the income inequality increases, maybe the graph may become like this. Okay, so only 10% of the people or will occupy maybe 90% of the wealth, like that. But these are examples of Pareto principle. Okay, so long tail distribution in user engagement. For example, in web analytics, the distribution of website traffic of follow Pareto principle, and 20% of the user account for 80% of the page views. So this kind of analysis is done for each unique user, how many pages they view on their portal. That is called engagement, because just visits to your website are not enough. You have to check how much your user is engaging with your website. Okay, so when a user just visits and immediately within just 2-3 seconds if he browses to other website, then that is not good engagement. But it is seen that 20% of the users account for 80% of the page views, and therefore for any marketing discount offer, etc., you should offer the incentives to those 20% of the users. And now you know the importance of that click stream analysis and everything, because how the company will know who is engaging how much. Okay, so who is viewing how many pages. Okay, who are the 20% users who are viewing maximum number of pages on your website? Obviously, they have to track your browsing behavior, right? So in the privacy policy only, which we often click next without even thinking that I agree. You have agreed that they will track your browsing behavior, right? Okay. So, and sometimes many browsers provide anti-tracking facility and all that. But remember that tracking is not always bad. Okay, if it is for a banking or financial site where you are doing your online transaction, there it might be some tricky issue. And even there also, tracking can help you finish your transaction in more secure manner. That means a fraudulent person who somehow successfully logs into your website, then his behavior can be flagged if your profile is created and that person behaves in a different manner. But that is a different thing. But in many of the websites, particularly service sector oriented websites, if you enable tracking, then they will be able to give more relevant content for you. Okay, and particularly those websites whom you trust and those websites which you engage with daily, for them you should always if you trust it, then you can allow tracking. Then they will give you most attractive offers. Okay, Cauchy distribution. Cauchy distribution is also continuous distribution with heavy tail. It is also a distribution just like this Cauchy. Okay, so it is continuous distribution with heavy tail only, like chi-square, like this chi-square. This is Cauchy. Okay, so and what is its use? So it is used in testing of machine learning model, particularly for outlier detection. Cauchy distribution can simulate data sets with extreme values, and then they test the robustness of models, particularly regression models which are sensitive to outliers. Because we have talked about these outliers. We have talked many times about when outliers are to be removed, when outliers are the actual cases of importance. For example, in credit card fraud detection or cancer detection, it is outliers who are important. So outliers cannot be blindly removed. You have to handle them very carefully. Now the question is, suppose I have made a model for credit card fraud detection and I don't have the data of actual fraud. So will I wait until some 20 or 100 frauds occur with my bank and then deploy my model? No, I will create a synthetic data in which some outliers are there and I will run my model on that synthetic data, because the condition is the only thing that your model while training should not have seen that data. So I can create an unseen data, synthetic data, simulated data set with extreme values, and I can test the robustness of my model. Robustness means my model should be able to handle those outliers without sacrificing with accuracy, precision, recall, etc. parameters, right? So Cauchy distribution, if here I want to show, then this is the Cauchy distribution, right? And if you again adjust some parameters, I think here maybe only this theta and sigma can be arranged. So you can adjust the tail on this side or tail on other side using this theta, and sigma is just a standard deviation. So low standard deviation is thin graph, and high standard deviation means high variance, that is a wide graph, like that. Okay, theta is the important variable because that decides the tail. So if I have to create a tail on higher side, for example, credit card fraud detection algorithm, where these are all transactions in $1,000. So anywhere in this region, more than $20,000 transaction in one transaction, that is considered suspicious transaction, right? So then that has to be taken care of. here also you can use this simulate and see over a period you will see that kind of Cauchy distribution created with this value of theta and with this value of sigma, right? I am not showing it, but you can try it using that link. Then logistic distribution. Now logistic distribution resembles normal distribution, so but it has heavier tail. Now here I think logistic perhaps would, yeah, this is the, so you can see it is almost like bell curve, but on tail side, on either end side, it is having heavier tail. Okay, so that is the logistic distribution. And what is its real life example? This is very popular example with which we start our discussion of classification. Just like we start our regression discussion with OLS, ordinary least square regression, we start our discussion of classification with logistic regression. So in binary classification problem, logistic regression assumes that the log of odds of the target variable follow a logistic distribution. Now don't worry about this sentence, because as I told that you have to learn this binary classification using logistic in much detail. So this we will see at the time that log odds of the target variable follow logistic distribution. But let us find here logistic distribution. So logistic L, yeah, here it is. So this is logistic distribution, and these are the equations for logistic distribution, and you can find that this is how it can be heavy tail. This changes only the mean value from 0 to other side, and here also this changes the mean value, right? Okay, so I'm putting mean at 0 only, and this changes beta. So beta changes the width of logistic distribution, but it remains like this. Its cumulative distribution function is like this S curve. This is often called sigmoid curve, and that is called logistic curve also. Okay, so this is the cumulative distribution function. It is very important function because in classification, because of one reason. Say this probability distribution that varies from minus infinity to plus infinity. Okay, but its cumulative distribution that just varies from 0 to 1. And if you remember, probability also varies from 0 to 1, right? So if I select these as my boundary for classification, and I say that any variable above this boundary is probability positive or successful event, and any variable below this boundary, below means it can be here also or here also, on the right side of this blue curve, that is not successful. So for example, if I am studying customer churn, whether my customer will go to my competitor or not. So if his data point prediction comes out to be in this region, then I will say that he will churn. In this region, then he will not churn, and so on. And the advantage with this logistic curve or sigmoid curve is that it can easily model the probability, because probability also varies from 0 to 1, and that is 0% to 100%. And the logistic regression sigmoid curve also has minimum value 0 and maximum value 1, while here minimum value was minus infinity and maximum value was plus infinity. This is the logistic log of that function, and we will see how this is obtained. This is obtained from this. Okay, so that we will see whenever we will study this logistic distribution in detail. But at present, just remember that what is its use? Binary classification. Then log normal distribution. Now log normal distribution is log normal distribution. That is this kind of distribution, and again I can vary my mu to make the mean changing slightly, and I can vary sigma square, that is variance. Okay, mu and sigma, they decide everything in statistics. So they decide various types of equations. Their equation may be different, but in every equation you have to put mu and sigma, and of course the value of x at which you are finding the value of fx, and plot the graph of fx versus f. Fx is y only. Okay, so instead of this fx you can write y is equal to, and then this kind of. So this is called a log normal graph. Okay, for various different values of mu and various different value of variance sigma square, right? So this kind of graph having tail on one side, that is log normal distribution. Again, log normal distribution is not much seen automatically in the data set, but sometimes there are data sets which are having certain distortion in shape like skew, etc. Then we do its logarithmic transformation and so on. So then we might encounter this kind of distribution. Then in a practical real life example, modeling salaries or house prices. Salary and house prices often follow this log normal distribution because it has two main characteristics. One, it cannot be negative. Salary also cannot be negative. House price also cannot be negative, right? And second, they have to have long tail. That means that there are always a few people who are extremely high paid in any company. The CEO and the vice president and etc. They are extremely high paid, and there are always a few people who are not that high paid, right? So that is one thing. And so tail is high. Similarly, house price also, there will always be few properties which only ultra rich people can afford, and therefore the long tail, this is called long tail, right? So long tail is one important characteristic. Now it is more pronounced long tail that you can see. Okay, is important characteristic of log normal distribution, right? Now T distribution is symmetric and bell shaped, just like normal distribution, but it has heavier tail. And T distribution has this use, hypothesis testing, especially when the sample size is less. Now hypothesis testing is the heart of data science, because in any problem, first thing you have to decide is make a null hypothesis and make a alternative hypothesis and then proceed further. That is converting your business problem into your data science problem, right? Now here, for small sample size, as such there are t-test and z-test and many different are there, but for small sample size, t-distribution helps a lot. Okay, so here let me first show you t-distribution. So I think this is that. Okay, yeah, it is like normal distribution or Gaussian distribution only, but with heavy tails. That you can see that like this. If I go down now, it is not looking perfectly normal. Here it was looking normal, but now you can see that it is having far heavier tail on either side. Okay, so it is looking like bell curve, but actually it is having this kind of that distribution. And one more thing is this that while building confidence interval for mean differences in a data set with fewer observations, t distribution should be used rather than normal distribution. Now this is important thing because sometimes, very rarely, you will be given a data distribution which has only few observations, and at that time, rather than trying to force a bell curve or normal distribution curve, you can use the t-test for hypothesis testing, right? And you can then use maybe t distribution to test your hypothesis. So this kind of distribution is more helpful when the data set is very small or you have less number of data points. Okay. Now here there is some more discussion about all these distributions. Okay, but that most of these things, not most, but I think discussed everything. So we will directly discuss only the code example. So what I have done in this part is, some people may find that unnecessarily same discussion is being stretched again, but it is not like that. I wanted to show that this type of data distribution actually occurs. By a code also you can set up and create that kind of distribution. Okay, so we will try to create some various data distribution using synthetic data in our example, but that would be next lecture. Thank you.